All right, everybody, welcome to the video here for lesson number 3. We're calling it the what power function. The reason why we're calling it the what power function is that sounds a little bit less scary than when we say logarithm. But we're basically doing the same thing here. So for us to get started here, we first have to figure out kind of how this function works. Then we'll talk a little bit about the function, and we'll start to solve a couple logarithms. So it says, today in our class, we're going to consider the following examples of the what power function and try and determine how it's used. So looking at these two functions, what we want to be able to see here is how are they used, right? So it says what power with a base of 2 of 8 equals 3, and what power with a base of 3 of 9 equals 2. So go ahead, think about that for a minute and then see if you come up with the same answer I have. All right, so now that we've all thought about it, I'm hoping you came up with the same reason that I have. So when I see the what power on 2 of 8, I'm saying 2 to what power makes 8? And the answer to that question is 3. So I'm saying 2 times itself 3 times is going to make the value of 8. For the next one, the same thing happens. So when I see a what power with a base of 3, I'm saying 3 to what number makes 9? And the answer to that again was 2. So we see that our what power function is essentially solving for the exponent. Let's see if our discovery kind of works here. So what power on 6 makes 36? The answer there should be 2. That's kind of an easy one. What power base 2 of 32? So we're going to say 2 to some number makes 32. So that answer should be 5. This would be the point in the lesson where I'd say, go ahead, try the next few yourself or with your partner, try and compare your answers. So go ahead and do that. You can even pause the video here so you could try all 6 of them before I start talking again. So go ahead, try and pause the video, try these 6, and then come back. All right, so welcome back. So hopefully you got some answers for me. So we're saying 4 to some number makes 64. If you're not sure of that offhand, try your calculator, play around a little bit with 4 with an exponent. You'll see the answer is 3. 10 to some power makes 1,000. Well, we know 10 squared is 100, so this would be 10 to the third power. Quick trick with 10 to any exponent, whatever the exponent is, tells you the number of zeros. So like 10 to the fourth power would be 10,000 because it would have 4 zeros. That's just kind of like a little trick. The last 4 were a little bit tricky. So 9 to some power makes 3. 9 to some power makes 3. So we want to get smaller. So you might have tried negative numbers in your calculator, and that didn't work. What you probably want to try there, though, is a fraction. The fraction 1/2 is really the square root of 9, which equals 3. Remember, fractional exponents represent radicals. That's all going to come back here. Next one, what power on 7 makes 1? That answer is 0. We want 0 there because anything to the 0 power is 1. The what power on 2 makes 1/8? Well, here we want a negative exponent because not only are we getting smaller, but we're becoming a fraction. So you might have tried a couple different exponents in your calculator. The one that works, however, is -3. Type it in, see what you get. You're going to get a decimal, change it to a fraction, you get -3. 5 to some power is equal to the square root of 5. This one you might have been stumped on, but if you do one quick trick, it's a little bit easier. Notice I'm changing my exponent there on the square root to a fraction, and that makes it easy to see that this fraction is going to be 1/2. All right, so now that we know how the what power function works, let's discover a little bit more about it. So here are some things about the what power function that are going to be non-well-defined or not well-defined values, meaning we can't use them. So when I have a what power of 0 equals 7, so 0 to some power equals 7, this is not well-defined because 0 to any power is 0. So one of the things of the what power function that can't exist is we can't have a 0 as the base. Once we have a 0 as the base, bad things happen. We can't evaluate that, so we can't have it. The same thing happens to 1. When I say the what power on 1 makes 5, well, 1 to any power is going to be 1. Positive numbers, negative numbers, whatever you type in is going to be 1. So we could say 1 to any power is 1. So this is a not well-defined value, so we can't put 1 in that base either. Something else also happens with negative numbers. So when I say negative 2 to some power makes 8, we can't do that. The only way I can make 8 with a base of 2 is by making it to the third power, but since there's an odd number of values, that would give me a negative 8, not a positive 8. So we also don't want negatives down here in our base because they alternate from positive to negative, right? So they do not make a function, we'll say functional pattern, right? We can't go from positive to negative and create a function. It just becomes things that are a little bit weird. So what we're seeing here from these 3 examples is when we put something in this basic term of what power base b of x, the base itself has to be greater than 1. Not equal to, but greater than 1. So we could say b is 1.1, b is 2, 3, 4. That eliminates the 1, that eliminates the 0, and eliminates all the negative numbers. Let's look at a couple other things that we can't evaluate with the what power function. 2 to some power makes negative 4. Well, because this is a negative, the only way to make a negative using exponents would be to have an odd exponent, but I can't make it with a base of 2, so this is not well defined. Okay, so again, just like before when we set up here, right, it does not make a functional pattern. It's the same idea here, right? Negatives here do not make a good pattern. Right, it's going to go positive, negative, positive, negative. It's going to be hard to make a function there. Same thing happens here. 2 to some power makes 0. There's nothing that works there, right? One of the reasons why is all exponential functions have an asymptote line at 0, so all what power functions are also going to have an asymptote line at 0. So there's going to be some kind of restriction here. So the what power function is also going to be restricted at this value, the x value, and that x value is going to have to be greater than 0. 1 is okay, so unlike the base, 1 can be put there. I just can't put anything less than 0 or 0. It just doesn't work out for us. So let's go over to the next page. So next page, we're finally discovering that we're not really talking about the what power function. We're talking about something called a logarithm. So the word logarithm is just like the word exponent. It's just a name for the type of function that we're creating, right? So the definition of a logarithm. The definition of a logarithm is the inverse of an exponential function where the exponent is solved for. So all of these what power functions that we talked about, right? Let's go back a little bit here. So every single one of these, we're solving for the exponent, every single one of them, right? So one of the things that's nice about the logarithmic function is we're solving for an exponent, which is going to come up in this unit of study. Some characteristics. The base has to be greater than 1. The x value has to be greater than 0. There is a vertical asymptote line, which we have not talked about yet, but we will, but we're just going to add it here in the characteristics. Okay? And it is a one-to-one function, meaning it's a function. Okay? Some examples of a logarithm would be like f of x equals log base 2 of x. Basically, any base we could put there as long as it fits into these two characteristics. Some non-examples would be like y equals log base negative 2 of x. That doesn't work for us. So when we're evaluating a logarithm, we're asking what exponent on that base makes the value in the parenthesis. So for this first one, we're saying what value on 3 makes 9? And that answer winds up being 2. Take a minute and try the next 5. See if you can come up with the value for each logarithm using what we already previously did with the what power functions. All right, welcome back. Let's see if you got these right. And then I want to show you a little trick on the graphing calculator. So it says log base 2 of 16, that answer would be 4. Log base 5 of 5, that answer would be 1. Log base 49 of 7, that answer would be 1/2. Log base 2 of 1/4 would be negative 2. Hopefully you got all of these. And 3 to the 0 power would make 1, so log base 3 of 1 is 0. Now, if you are somebody that has a newer-ish graphing calculator, what I want you to do right now is hit the math button. The math button is off to the left. And then scroll all the way down and see if you have something that says log base. That's what it will say on your graphing calculator. If you have that, click enter. And you should be very excited because now you can type in each one of these logarithms and evaluate them. So the whole thinking process, well, it doesn't really matter to you because you could just type it in your calculator. If you're an old calculator person, you just have to remember a simple trick. So if you're an old calculator person, if you're a new calculator person, ignore what I'm going to say. But if you're an old calculator person, you just need to know that if you take the log of 1 and divide it by the log of 3, it'll be the same thing. This should give you 0 in your calculator. The log button is on the left towards the bottom. It's like next to number 7, I believe. So let's move on. So now that we know how to evaluate logarithms, well, that means we can now finally find the inverse of an exponential function, which we've been kind of trying to do now for a few lessons. So for this inverse, I'm going to say, all right, so I have x equals 2 to the y. Well, why is this idea of logarithms going to help us? Well, we know that every exponential function has an answer, it has a base, and it has an exponent. Well, every logarithmic function has an exponent. The word log to tell us what kind of function we have. It has a base, and then that answer is inside the parenthesis. So in this particular case, here are 3 parts, right? So we have our answer is x, we have our base is 2, and our exponent is y. So if I rewrite this as a logarithm instead of an exponent, I can say y equals log base 2 of x. So now how does this help us? Well, now that y is solved for, I can graph this. Eventually we'll graph logarithms in this class, right? Now that I have y solved for, I can figure out exactly what the exponent is if I know what the answer is, so I can work backwards. And I can now type this into my calculator to evaluate if I know the value of x. So let's find a couple inverses because this is a skill that is definitely going to be usable on Regents exams, etc. moving forward. So same rules apply. I see the word inverse, I switch x and y, but now I have to say, well, it's a logarithm, so let's change to a log. So I'll say y equals log base 3 of x. Since it's an inverse, that's also a function, I'm going to use function notation here and say f negative 1 of x, log base 3 of x. How do I know that this is going to be a function? Because the original function was 1 to 1. All exponential functions are 1 to 1. So if I do the same thing with g of x, I'm going to switch x and y, rewrite it as a logarithm. By rewriting it as a logarithm, we're not changing anything, we're just making it look different. then I can say g negative 1 of x is equal to log base 6 of x. So essentially what I mean by that, we're just making it look different, is these two expressions, these two equations, I mean, are the exact same function. We're just solving one for y, where the other one, y, is just floating up there in the exponent, right? So we're just making it look better by changing it to a logarithm. It's the same value, it's the same set of points, there's nothing different about it, it just looks different. So don't let the word log make you like stressed out about it. Try h of x yourself. All right, hopefully you paused the video and tried h of x yourself. If you did, I'm hoping that you switched x and y like the other examples. Resolve this using log, so we have log base 10 of x, and then you could even rename it to its function notation for inverse, log base 10 of x. Look at that. Look how nice that is. So now we can say all functions, if you look, can be solved for the base and everything else. So looking at each one of the four that we did, the exponential base became the base of the logarithm. The exponent itself became the y value, and the inverse's answer became the x value. So we can kind of say here is, if I was to make the inverse of this, it's going to become y equals log base b of x, where b is greater than 1. Now, not all inverses are created equal. These last two are a little bit tricky. So they're not just involving us changing from an exponential function to a logarithmic function. They're asking us to do some algebra too. So let's take a look at the first one. I see inverse, I think switch x and y. So I have 2 to the y plus 1. I want to get y by itself. So to get y by itself, I have to get the exponential part by itself. So I need to get 2 to the y by itself, which I've now done. By doing that, I now can say, all right, I can change this to a logarithm. I'm going to make the exponent what it's equal to. It's a logarithm of the base. And then whatever the exponent was equal to, that's going to go in the logarithm itself. There's my inverse. I could even say inverse notation, right? So we'll say log base 2 of x minus 1. That one wasn't too bad. To find the inverse for g of x, again, we'll switch x and y. So we'll say x equals 3 to the 2y minus 1 plus 7. I can subtract 7 from both sides. X minus 7 equals 3 to the 2y minus 1. Since I have the exponent part by itself, I can now rewrite this as a logarithm. So I can say the exponent, 2y minus 1, equals a log with a base of 3 of whatever that exponent was equal to, in this case, x minus 7. If I then add 1, I have 2y equals log base 3 of x minus 7 plus 1. Notice I'm always putting that logarithm piece here, this x minus 7, in a parenthesis to clearly separate the plus 1. I then could divide everything by 2. And I could say g of negative 1 of x, right? Function notation is equal to log base 3 x minus 7 plus 1 all over 2. That's a tough one, but definitely doable. Hopefully this notes video helped, and we can move on to your homework video. Again, they'll be posted together so you can kind of watch both individually, and we'll keep moving with this unit. All right, best of luck, and hope to see you soon.